we've got a piecewise linear function that's defined from -2 pi to 4 pi, and we're given that graph, the graph of g, and f is g of x minus cosine of x of 2. So first off, we're looking for the integral for part A. If I could write, I need my pen, not a little selecting tool. Come on. There we go. All right, so for part A, we're going to integrate from -2 pi to 4 pi of f of x, which is g of x minus cosine of x over 2. And so for g of x, that's just the integral from -2 pi to 4 pi of this function that we're looking at here. And so that ought to be, let's see, this is a total of 6 pi, and this is a total of 2 pi. So multiply those together and divide by 2 ought to give you 6 pi squared for the g of x part. And then the integral of cosine of x over 2 ought to be a minus 2 sine of x over 2. And we'll have to evaluate that from -2 pi to 4 pi. And let's see here, that's the sine of 2 pi, and that's going to be the sine of -pi, which is all just going to be 0. So this just becomes 6 pi squared minus 0, which is 6 pi squared. So that's part A. And just to give people the point breakdown in case anybody was having difficulty with that, it was 2 points, one for the right antiderivative here, and one for the final answer there. Everybody good there with A? No. So you're asking though about parts B. Oh, where did I get the 6 pi one more time? So the 6 pi squared here, it's just the area underneath this curve, the graph of g. That's the integral of g from -2 pi to 4 pi. And so, that's just, this is a length of 6 pi from -2 pi to 4 pi. Triangle has a height of 2 pi, so 6 pi times 2 pi. And then it's triangle, so 1/2 that. Cool. Yep, no problem. All right, everybody good with A now? All right, so for part B, I'll start, I probably have to go to a new page for this, but start here. For part B, we're looking for all x values on the open interval 2 pi to 4 pi for which f has a critical point. So f has a critical point whenever f prime is 0 or whenever f prime is undefined. Well, first off, what is f prime? F prime is g prime, and then derivative of cosine of x over 2 ought to be plus 1/2 sine of x over 2. So we are interested in when is this undefined and when is this thing equal to 0. So first off, anywhere where the derivative of g doesn't exist between -2 pi and 4 pi, this whole thing will be undefined. So g prime we know is undefined at x equals 0, right? Because we have a corner there. So there's one critical value that we potentially have. And then we have to sort of take a look at what is g prime. Well, g prime changes from -2 pi to 0. We'll just say on -2 pi to 0, g prime is equal to 1, right? That's a slope of 1. It's got a rise of 2 pi, a run of 2 pi, slope of 1. But on the interval from 0 to 4 pi, g prime equals, and this is -1/2, right? And so we need to take that into account as we're looking for times at which this is equal to 0. So let's see if we can write this out. We've got 1 plus the sine of x over 2, and we want to know if that ever equals 0. And we're
1/2 sine x over 2.
What? Oh, 1/2. Sorry. Thank you. And that's what happens when I go from page to page. 1 plus 1/2 sine of x over 2. And so we're looking to see if that ever equals 0. So that would mean that 1/2 of the sine of x over 2 is equal to -1, or the sine of some angle is equal to -2. Well, this is never true, right? Never take the sine of something and get a value that's less than -1 or greater than 1. So that's never true. And then we'll do the same thing with, what was the other one? It was -1/2. See if I can do this right, the right thing this time. -1/2 plus 1/2 sine x over 2. We want to figure out when that equals 0. So we'll add the 1/2, which will give us 1/2 sine x over 2 equals 1/2. We'll multiply by 2 to get sine of x over 2 equals 1. And then sine is equal to 1 when the angle is equal to pi over 2. And then it's pi over 2 plus any 2 pi n, right? Because we get 1 every 2 pi. So when we multiply this by 2, this is x equals pi plus 4 pi n. And so we're looking, remember that this piece over here was from 0 to 4 pi. And this piece over here was from -2 pi to 0. From 0 to 4 pi, well, if we plug in integers for n, if n is 0, we get pi. If n is 1, we get 5 pi. Well, we can immediately eliminate 5 pi because that's not on the interval 0 to 4 pi. So we have a critical value of x equals pi as well as x equals 0. So 2 critical values. And the point breakdown for that was, let's see here, maybe 1 point for correctly taking the derivative of cosine of x over 2, 1 point for correctly having a value of f for f prime, which was g prime. Sorry, no. Let's say g prime of. Oh, they just gave you 1 point for literally having g prime in there and 1 point for having the derivative of cosine of x over 2 correct. Then they gave you 1 point for getting x equals 0, and they gave you 1 point for getting x equals pi. That makes sense for part B for everybody. It's kind of a little bit of a complicated one, but. No other questions on part B? Then we'll move to part C. All right, so for part C, we've got h of x, which is the integral from 0 to 3x of g, so just the integral of this from 0 to 3x. We want to find h prime of negative pi over 3. So if h of x is the integral from 0 to 3x of g of t dt, let me make sure I got that written down right? 0 to 3x of g of t dt, good. First off, let's find what h prime of x is so that we can then evaluate it at the value they asked us to. So this is the derivative of the integral from a constant to a function of some other function. So when we take the derivative of this, it needs to become just this function evaluated at the function there times the derivative of this function on the top. That's our first part of the fundamental theorem of calculus. Right? It's just g of u times the derivative of u when we take the derivative of this integral. So there's h prime of x, and we want to evaluate that. I believe it was at negative pi over 3. If that's wrong, somebody tell me. But I'm going to move forward, assuming that's what I think that's what it was. So now we're looking for g of negative pi. So we have 3g of negative pi and g of negative pi. If we go back up here, this is the graph of g. Negative pi would be right here. Well, if this is a slope of 1, I've gone to the right pi, so I must have gone up pi. So this is the point, negative pi, pi. So g of negative pi ought to be pi, and our answer ought to be 3 pi. And they give 3 points for this one, 1 for the answer, and 1 for the correct H prime value. Any questions there? Is that helpful? Everyone's good with 9, B, and C, and A now? All right, I'll assume that's a yes, since I'm not getting anything in the chat. All right, any other questions on the graph FRQs before we move on to the multiple choice? Cool. All right, in that case, let's move on to the multiple choice. Just, I guess, type whatever questions you might have from the multiple choice into the chat, and I'll just go through them as we get to them. Looks like we're starting with number 7. Oh, man. Trista, I wish you'd said that first, because I have a mild compulsion to start at the beginning here. Wish we'd started at 1, but it's too late because 7 was said first, and now I have to follow that. But we'll come back to 1 in a bit. All right, so, oh my, all right, we got lots of questions here to do today, don't we? Number 7. All right, so number 7, we got an integral from 0 to 6 of the absolute value of x minus 4 dx. So for this one, you just need to know what the graph of the absolute value of x minus 4 looks like. And so, I mean, there's no way to integrate absolute. We don't have a way to integrate absolute value. We just have a way to graph it and find the area underneath that curve. So the absolute value of x minus 4 is just, here's 4. It's just this, right? And so if we're going to do this from 0 to 6, we're just looking for this area plus this area. Absolute value of x minus 4 means this is a height of 4. If this is a length of 4, right? It should cross at the same places. And if this is 2, then this is 2. And so this should just become the area underneath this curve. So 1/2 of 4 times 4 plus 1/2 of 2 times 2. Which should come out to be, what is that, 16, that's 8, and then that's 2, so it looks like that's 10. Any questions there on 7? Everyone good on 7? Okay. Next one will be 19. So for 19, we got a rectangle. Let's see, we got a rectangle with one side on the x-axis is inscribed in a triangle formed by y equals, I can start the triangle. Oh, that's not y equals x. That's bad. Y equals x, y equals 0, so the x-axis, and then 2x plus y equals 12. What is that? Y equals negative 2x plus 12. Oh my, okay. Something like that. This is 12. This, if that's negative 2x, then that would be 6. So we got a triangle, and then we got a rectangle with one side on the x-axis inscribed in the triangle. So looks like that should look like my triangle or my rectangle in a different color. Something like that. Wow, my rectangle is atrocious. Something like that. All right. So what do they want us to find? The area of the largest such rectangle. So we want to maximize the area of that rectangle. Okay, so let's think here for a second. Our area, let's see here, our area of that rectangle should come from whatever this length is times whatever this height is. And so we'll just call it length times height. Our length in terms of x values should always be whatever this x sub 2 minus, we'll just write x sub 2 minus x sub 1 to start with. I'm calling that x sub 2 and that x sub 1. And then our height is some y value. And let's see if we can write x sub 1 and x sub 2 in terms of y. And if we can do that, then we should be able to write this all in terms of the single variable y and then solve it by taking a derivative for it. And so I think, Krista, I saw you'd ask later on about this. Also, yes, you do need a derivative to solve 19. So somebody else had already asked about this one, but to answer your question, yes, you need a derivative. So let's figure out what x2 is. So this is the x value when my what was it, 2x plus y equals 12. And so that would be x equals 12 minus y over 2. So any x value here is 12 minus y over 2. So we'll have 12 minus y over 2 minus, and then this x value, if y equals x, is just y, and then times y. So this is our function that represents the area. And we can simplify that down. This is 6 times the y, so that's 6y. And this is minus y over 2 minus another y, so that's minus 3y over 2, so minus 3y squared over 2 when we multiply by the y there. And so then our derivative, a prime, ought to be 6 minus 3y. And that equals 0 at a potential max when y is 2. So the theory is that y equals 2 will work. We need to make sure, though, that that's actually a max. So I'll put on 2. We're not going to have y values that are less than 0, right? And we're not going to have y values that are greater than whatever this intersection point is. So if y equals x and 2x plus y equals 12, we need to replace the x's with y. So that would give us 3y equals 12 or y equals 4 is where those intersect. So we don't want to put anything larger than 4 into that when we test. So if we test something like 1, we get a positive. Increasing, we test something like 3, we get a negative. Decreasing. So we can see that it is a max when y is 2. And I assume it asks for the actual maximum area. Is that right? Let me read back here. Yeah, the area of such largest triangle is that. So we'll just put in the 2. 12 minus 2 is 10, or 2 is 5 minus 2 times 2 ought to be, looks like 6. Choice, what choice is that? Choice A. Alternatively, you could have gone down here and used the second derivative test. And so the second derivative is -3, which is less than 0. And if at a critical value where the derivative is 0, your second derivative is negative, tells you that it's concave down, which tells you that it must be a max also. So you could use the sign chart or the second derivative test. If this was a free response question, you'd have to demonstrate why it's a max. So either one of those would work. Any other questions on 19? Everybody feel okay about that or no? All right, next one is 41. Not going too far. Okay. 41. All right. Okay, so this one is similar to ones we had done previously. I think I mentioned that I can't imagine, I've actually never seen this put on there. This is just like sort of getting you ready for the second semester of calculus, Calc 2, Calc BC, Math 151, whatever the heck they call it. I didn't mean to put that line, but that means something different. So we want to substitute x equals tangent theta. And so if for some reason they ask you to do this, I know we never covered this because it's not something that I've ever seen asked on the AP test. If they do ask you to do this, make a weird substitution like this, just make sure you convert your dx into the d theta properly by taking the derivative of your x that they're asking you to substitute. So the derivative of tangent is secant squared. So dx will be replaced with secant squared theta d theta. So this becomes an integral from the tangent of 0, or sorry, yeah, so if 0 equals tangent theta, then theta is 0 for a lower limit, and if 1 equals tangent theta, theta is pi over 4 for our upper limit. And so we have 0 to pi over 4 of the square root of 1 plus tangent squared theta times secant squared theta d theta. 1 plus tangent squared theta is equal to secant squared theta, and the square root of secant squared is secant. So secant times secant squared is secant cubed. And that's something you'll have to do if you take the second semester of calculus next year, is do this thing. It's called an inverse trig substitution to turn something like this that you can't easily integrate into something like this, which also actually doesn't very easily integrate. You have to use another method that you learn in second semester of calc called integration by parts to integrate that, but that's a different story. At least you can integrate it now. You will be able to once you do that. So it looks like that was choice D, I think. Is that right? Yeah. Anyway, is that good? Any questions there on 41? No, everyone's good there. Okay. I hate to do this. We're going to go to 85, and then apparently right after we're going to go back to 84, which is going to drive me insane. Instead of doing 84 and 85. But all right, we've got, let's see. All right, so for 85, we're looking at a smokestack that is 100 feet tall. And the diameters are shown in the table. So hopefully you're looking at the table on the worksheet right now. Let's see, here's our height. Here's our diameter. That's 100, 75, 50, 25, and 0. And this is 5, 7, 9, 15, 17. And they want us to use the midpoint rule with 4 subintervals to estimate the volume of this to the nearest 100 cubic feet. So we need, if those are the diameters, the volume should be, each of those diameters that we're looking for, we'll need to turn them into a radius and find the area of that cross section, because we're going to sum together the areas of the cross sections, right? That's what we need to do. The area of the cross section is pi r squared, and so we'll need to sum together those. So we'll have to take half of each of our diameters, and let's see here. Oh, use midpoints. Okay. Okay, yeah, it makes life easier. So we'll start from 0 to 25. So from 0 to 25, we've got pi. We're going to have pi for all of these, and the length of each interval is 25. So we're going to have 25 pi times each of these, and then it should just be the radius squared for each one. And so the first radius should be halfway between this, because we're using a midpoint. Halfway between that is 16, and that's the diameter, so the radius ought to be 8. halfway between 15 and 9, that ought to be 12. So half of that will be 6. Halfway between 9 and 7 will be 8. Half of that will be 4. And halfway between 7 and 5 will be 6. And half of that will be 3. So what do we got? We got 64 and 36. That's 100, 116, 125, 125 times 25 pi. I don't even know. It's 125 times 25 pi. So I think this must have been, what does that come out to be? I think it comes out to be closest to about 9,800. I don't know. Do they give you a calculator to approximate that?
Yeah.
These ones are, yeah. So just, yeah, I think that's right. That sounds right to me. If I multiply 75 by the 125 and add a little to it. Hopefully that's what it said the answer was. If not, then I just arithmetic wrong. Is that what the answer it said was?
Yeah.
Oh, good. Cool. Any questions there on 85? All right, so we'll move back to number 84. Number 84 gives us this graph of 4 over x squared plus 1. The max there is on the y-axis. My graph is just bad. It says we've got capital H of x, which is equal to the integral from 0 to x of f of t dt. This is 4 over x squared plus 1, which is f of x. And it says the local linearization of h at x equals 1 is what we're looking for. So we are just looking for a linearization formula here. So if we remember back, linearization tells us, let's see, we're looking for capital H. So the linearization of capital H should be the value of capital H at 1. So this should be the integral from 0 to 1 of 4 over x squared plus 1, right? That's what we're looking for. And we're trying to use a linearization to approximate that. And so let's see, linearization formula. We're doing that at, like I said, we're doing that at 1. So it should be so if we evaluate this, let's write our linearization. The linearization at 1 should be h of 1 plus h prime of 1 times x minus 1. And so h of 1 is this, integral from 0 to 1. The integral from 0 to 1 of this should be 4. The integral of 1 over x squared plus 1 is inverse tangent x from 0 to 1. So that's 4 inverse tangent 1 minus inverse tangent 0. Inverse tangent of 1 is pi over 4. Inverse tangent 0 is 0. So h of 1 is pi. And then h prime of x is just equal to f of x. And so if we look for what is the value of f of x at 1, f of 1 ought to be 4 over 2, which is 2. So it should be pi plus 2 times our x minus 1 value. So that's just our linearization formula. Linearization is the value of the function at your center of approximation plus the derivative of your function at your center of approximation times x minus your center of approximation. And since we're doing it at 1, 1 is our center of approximation. Any questions there on 84? Does that make sense or no? All right. Back now to number 1. Let's see here. Maybe I can find it. All right, number 1. We want to know which of the following functions is continuous at x equals 0. So our first option is sine of 1 over x when x is not 0, and 0 when x equals 0. So for that to be continuous at x equals 0, for anything to be continuous at x equals 0, the limit as x approaches 0 from the left needs to equal the limit as x approaches 0 from the right, which needs to equal f of 0, which in this case is 0. So here, as we approach 0 from the left, what happens to sine of 1 over x? Sine of 1 over a very small number becomes the sine of basically negative infinity, right? Well, what happens as you try to take the sine of negative infinity or the sine of positive infinity is as sine goes towards negative or positive infinity, this oscillates, which means that it does not exist. Does not exist is not the same thing as 0. So the first one is not continuous. Everybody good with A not being continuous? Okay, B is your greatest integer function, which you should have seen once or twice this year. Right, greatest integer function looks like this, and so on. It's your step function. So clearly this one is not continuous at x equals 0. The limit from the left is -1. The limit from the right is 0. So not continuous. Parts. Their question C says x over x if x does not equal 0, and 0 if x does equal 0. Well, x over x is just 1, right? So this should look like 1 on both sides of 0, but 0. Well, that's clearly not continuous. And then D gives us x sine 1 over x for x not equal to 0, and it gives us 0 for x equal to 0. So we need to find the limit as x approaches 0 from the left of x sine 1 over x, which we've proven this one earlier this year. We did this by the sandwich theorem. That equals 0, as well as we'll say from the right and from the left this equals 0, which means the limit as x approaches 0 of this is 0, and that equals 0, which is what it equals at 0 according to this. And so we'll say yes, that one is continuous. And then just for E, we can see that E, which is x plus 1 over x, that one's got a vertical asymptote at x equals 0. So that one's definitely not continuous there. You guys remember doing this proof of these limits by the sandwich theorem for part D? Anybody need me to go through those limits for D to show that that equals 0? Okay, nobody miss anything, so I'll assume that's a no. We'll move on to the next one. Next one is number 4. All right, number 4, we got the x-coordinate of the point on the curve y equals x squared minus 2x plus 3, where the tangent, we want the tangent line perpendicular to x plus 3y plus 3 equals 0. So we want the tangent line to this to be perpendicular to this. So first we need to find this slope. So that's negative x minus 3 over 3. So the slope here is negative 1/3. So the slope of a perpendicular thing to this ought to be positive 3. So we are looking for, when does the slope of this equal positive 3? Slope of this is the derivative, so 2x minus 2 equals 3 when x equals 5 halves. Any questions there on number 4? All right. Next one, number 11. Turn the page here in this book. All right, number 11. We've got the integral from 0 to pi over 2 of cosine squared x sine x dx. So this one you should recognize as a u substitution integral. We're going to let u equal cosine x, and then du will be negative sine x dx, which means we'll put in a negative and a negative. So we've now got negative, and it's negative of the integral from, since we're doing u instead of x, the cosine of 0 is 1, so our lower limit will be 1, and the cosine of pi over 2 is 0, so our upper limit will be 0. And this will become, since it's cosine squared, it'll become u squared, and negative sine x dx becomes du, so we got u squared du. And if we want to make this a little bit easier, we'll flip our limits and get rid of the negative sign. So this is just the integral from 0 to 1 of u squared du, or u cubed over 3 from 0 to 1, or a third minus 0. Looks like that's choice D. Any questions or issues there on number 11? Any other questions on 11? All right, next one we are looking at here is 51. Maybe. All right, 51, we've got an integral from 2 to 4 of du over...
Mr. Bachelor?
Yeah.
I just realized that I asked for that one, but that one's in the BC only section.
Oh, yeah, it is. All right, well, we don't need to worry about that one then. Yeah, good thing. You would have all been really confused when I started talking about doing an inverse trig substitution to solve that. Oh, well. All right, we don't need to do 51. So let's see here. Let's look at what's next here. Number 7. All right, number 7. Oh, we already did 7, right? Yeah. Did that one earlier today. Next one is 17. Oh, perfect. All right, so for 17, we're looking at the function f of x, which is equal to x squared if x is less than or equal to 2, and 4x minus x squared if x is greater than 2. We're looking for the integral from -1 to 4 of f of x. So in order to do this one, since we've got a discontinuity, well, I don't know, check to see if we have a discontinuity, but because we have a piecewise defined function, we have to split it into two different intervals at the point where it changes. So from -1 to 2, we'll just integrate x squared. And from 2 to 4, we'll integrate 4x minus x squared. So we'll have x cubed over 3, -1 to 2, and we'll have 2x squared minus x cubed over 3 from 2 to 4. And you'll just go through and evaluate all that. So that becomes 8/3 minus a -1/3, and then plus, we got 32 minus 64/3 minus 8 minus 8/3. And I don't know, you get whatever you get with this. So let's see, that's 9/3, so that's 3 plus 32 is 35 minus the 8 ought to be 27 minus 64/3 plus 8/3. What is that? That's 56/3. So 27 minus 56/3, which ought to be, let's see, 3 times 27 is 81. So I guess that ought to be 25/3. Hopefully I did all that arithmetic right there. Yeah, that's an answer choice. So hopefully it's the right answer choice. Is that what you all got? Or is that what it says C is 25/3?
Yeah.
The right answer? Yeah. Perfect. I did my arithmetic right. Yeah, so anytime that there is a split in a piecewise function in the middle of your integral, just split it at that point and do each piece separate. Any questions there on 17? All right, next one is 19. I think we did 19 already. Yeah, next one is 20. So we'll do 20 next. Let's see, we got the x value of the first quadrant point that is on x squared minus y squared equals 1 is closest to the point 3, 0. So x squared minus y squared equals 1. It's first quadrant point closest to the point 3, 0. So in order to figure that out, we're going to have to write a formula to represent the distance between the 2 points, and then we will minimize that distance. So it doesn't really matter what this function looks like. We know that the distance between any point on this function, which we'll just call x comma y, and the point 3, 0 ought to be the square root of, we'll say, x minus 3 squared plus y minus 0 squared. All right, so that's the distance between these two, between a point here and a point here. And what we'll need to do is we'll need to go in and replace either our y's or our x's. It makes more sense to replace the y's with x values just because we have a y squared here and we have a y squared here. So we can see that y squared is equal to, we bring that over and then subtract the 1, x squared minus 1. So this is the square root of x minus 3 squared plus x squared minus 1. And you just need to minimize this. Now, that's sort of an unpleasant thing to take the derivative of and deal with. But if you remember, we can minimize the square of it. We talked about this back when we were doing our optimization problems, the minimum of a function, we'll just say the thing inside of here, is at the same x value as the minimum of the square root of that. So we're going to take the minimum of the square of this and just figure out at what x value that's true. So we're going to just find the minimum of x minus 3 squared plus x squared minus 1. And that ought to be 2 times x minus 3 times the derivative of x minus 3 plus 2x plus 0. So this becomes 4x minus 6. We want to see when that equals 0. And that should equal 0 at x equals 3 halves. And we can test that and make sure that it's a minimum, plug something in between 0 and 3 halves, like 1 into our derivative, we get a negative, so decreasing. And plug something greater than 3 halves in, like 10, we get a positive. So it's definitely a minimum. So that minimum occurs when x equals 3 halves, which is choice B. Any questions there on number 20? All right. Next up is 22. So we got the region bounded by y equals x squared and y equals 6x minus x squared. And we're going to rotate that around the x-axis. Gives you rings. That's nice that they tell you that. The value of x for which the ring of largest area is obtained is. So we are, first off, let's just make a quick sketch of this. Here's y equals x squared. And then 6x minus x squared ought to have an x-intercept at 6 and look something like this, probably facing down. And so when we rotate that around the x-axis, the region between, we're looking for when is the vertical distance between these two functions at a maximum, because we want the largest area. If the radius of that, we're looking for, see what the value is, the ring of the largest area. So we're just looking for something that represents the area as we revolve this around. The area of each ring ought to be the outer radius, which is 6x minus x squared. The area is pi times that minus the inner radius, which is just x squared. And so we are interested in when is that at a maximum. And so in order to figure that out, we'll need a derivative. Probably better to distribute this out first, maybe, to get your derivative. That's our, everybody good with that being the area of a cross section? That's just from like our volume area unit.
I just have one question. Why would we be multiplying it by pi? Because it's a ring, so it's like hollow in the middle. And so would you be able to do the area with, like, because did you multiply by pi because of pi r squared?
Yeah, because I mean, so this is a ring, right? It's a ring with a ring inside of it, or a circle with a circle cut out of it. So it's pi times the outer radius squared minus pi times the inner radius squared.
Oh, okay.
Area of the outer one minus the area of the inner one. So I just
Okay.
Good?
Yeah, thank you.
Mm-hmm. So if we distribute all of this junk out, 6x times 6x, 36x squared, it's going to give us a minus 12x cubed. This is going to give us a plus x to the fourth, and this is going to give us a minus x to the fourth. So those will cancel out. So our area is just this times pi. So our derivative to find the max should be just pi times, this will become 72x minus 36x squared. The pi, and the pi is insignificant in here because it's not going to affect when this thing equals 0. So we'll just take this and 36x squared. I should probably I'll just take the 36x out of it, and that gives us 1 to 3. That gives us a 2 minus x is equal to 0. So that'd be either x equals 0 or x equals 2. But x equals 0 clearly doesn't make any sense because that's where they intersect. So that's going to probably be our minimum. And x equals 2 ought to be our max. We can prove that's a max in 2 different ways. One is with a sign chart, which we've been doing. The other is with a second derivative. So let's do the second derivative since we only did that once. A double prime ought to be pi times 72 minus 72x. And if I plug in 2 to that, a double prime of 2 is less than 0, which indicates that the function is concave down and that it has a max at that x equals 2 value. Any questions there on 22? All right, next one. Hold on 1 second. Okay, sorry, that was 22, right? Yeah. All right, next one I got here is 26. All right, so for 26, it says we're going to estimate the integral from 0 to 4 of root 25 minus x squared using a left rectangular approximation. We're going to use 2 subintervals of equal width. So we just want 2 subintervals. So that just means we're going to go from 0 to 2, and then we're going to go from 2 to 4, which means we need the value of this at 0. So the value of root 25 minus x squared at 0 is 5, and the length of that interval is 2. So that's the first piece of it, and the second piece of it is again 2, and then the value of this at 2, which is root 21. So it looks like it's just 10 plus 2 root 21. I guess we can write that out. Good or no? Just a left rectangular approximation. Any questions there on 26? All right, next one is 30. All right, 30 says the number of values of k for which f of x equals e to the x and g of x equals k sine x have a common point of tangency. Okay, so we are, we're trying to figure out, let's see here, trying to figure out when they have a point of tangency. So when, basically when they touch each other but bounce off. Let's think about this here. What do we need to know here? We know, let's see if they're gonna, first off, we know that they need to equal each other, right, at that point. So we know that e to the x needs to equal k sine x. And we also need the, let's see, yeah, we also need their slopes to be equal there. So we're going to have, if they both have tangent lines at that same point, then we need the slopes. Yeah, that makes sense. Okay, so they're the same. It does say, what does it say here? Let me just reread this again. Yeah, common point of tangency. Yeah, so we need the slopes to be the same also. So that means that e to the x, which is f prime of x, needs to equal g prime of x, which ought to be k cosine x. So we need to figure out when does e to the x equal k sine x, and when does e to the x equal k cosine x. Well, if they both equal e to the x, that just means it happens when k sine x equals k cosine x. And we can just divide by the k's to say this is true when sine x equals cosine x. And that should happen when x equals pi over 4. And let's see here. Guess we could say 5 pi over 4. No, 5 pi over 4 is not going to make sense. We're going to do the negative 3 pi over 4 version of this, which is the same as 5 pi over 4. Did they give you a calculator for this one, or no? Is this in the calculator section? This was before the calculator, right? Before they said use a calculator. Yeah, okay. Yeah, so they have pi over 4 and negative 3 pi over 4 for that. And I believe, let's see here. Yeah, so that just would be 2. No, not 2. Because this shouldn't, yeah, because this keeps occurring. So this keeps occurring, right? Pi over 4, negative 3 pi over 4. 5 pi over 4. There should be an infinite number of places where this occurs. What was that? 5 pi over 4, 9 pi over 4. So we should get it. We should get an infinite number of these. That's a tough one. I've never seen anything that difficult on there. So I wouldn't be too concerned about that one. But yeah, just note that this has infinite number of solutions. There was no restriction on the domain, so this will continue happening over and over and over and over again. Good or no? All right. Let's see, 19 and 20 we already did. Did we do 22 already? We did 22. Did we do 6? 6 is the next one. No, we did not do 6 yet. All right. So for number 6, we are looking at polynomial function p. We're given p double prime of 2 is negative 6. P double prime of 4 is 0. And p double prime of 5 is 3. We want to know which of these must be true. Okay, so it says that first off, p has an inflection point at x equals 4. That's a really enticing choice, but it's not the correct choice. It's enticing because you think that since at 2 it was a negative value for the second derivative, and at 5 it was a positive value for the second derivative, and at 4 it was 0, it must have changed concavity at 4, right, to go from negative 6 to 3. Well, it didn't have to change concavity here, right? They don't give you a value of p double prime of 3. P double prime of 3 could have been, 100. And p double prime could have been greater than 0, or greater than or equal to 0, let's say, for the interval from 3 to 5, in which case we definitely wouldn't have had a point of inflection at x equals 4, right? It doesn't give us this information. It doesn't tell us what the value of p double prime is on this entire interval. So we can't just say that it must have changed at this value. It could have changed somewhere else between 2 and 4, right? Or it could have changed somewhere between 4 and 5. So it looks like it, but not necessarily.
Okay, that was my only question for that question. So I understand now.
Okay. I'll sort of go through the rest of it. There's only one more question left that's been put in the chat, so I'll go through the rest of them just to make sure everybody's good there.
Okay.
But B says P has a minimum at x equals 4. That doesn't make any sense because the second derivative is 0, and that tells you when you might have a plane of inflection. So B is definitely a no. You can only have a max or a min if you have an actual value of your second derivative there. So that's a no. C, P has a root at x equals 4. I mean, for that one, there's no guarantee that it has a root. It's possible you could have a root at x equals 4, but that's another not necessarily that I'm just gonna scroll necessarily because it's got too many C's and S's and L's that for me to remember how many there's doubles of. And then D, P is increasing on 2 to 5. I mean, no. P is not necessarily increasing on 2 to 5 based on its concavity. Concavity does not indicate increasing or decreasing. So their statement that A through D are all false is a poor statement because they're not necessarily all false, but none of them are guaranteed to be true. So E would be the best choice there. Cool. Any other questions on 6? All right, and the last one we've got here is number 31. So number 31 says we've got 2x squared y plus y squared equals 2x plus 13. And we know that that passes through the point 3, 1. We want to use the line tangent to the curve there to approximate the value of y at x equals 2.8. So we need to take the derivative of this implicitly. So that becomes 2x squared dy dx. And we're doing the product rule. So first function derivative of second plus second function y times derivative of first 4x, so 4xy. And then plus 2y dy dx equals 2 plus 0. And then we're going to solve for dy dx. So dy dx ought to be 2 minus 4xy divided by 2x squared plus 2y. Here, subtract the 4xy first, then factor out the dy dx and divide by what's left. If we want to, we can make that 1 minus 2xy over x squared plus y, just to make life a little easier with the arithmetic. We'll evaluate that at 3, 1, which gives us 1 minus 2 times 3 times 1 is 6. And then x squared is 9 plus 1 is 10. So that equals negative 5/10 or negative 1/2. So the equation is y minus 1 equals negative 1/2 times x minus 3 using point slope form. We want to approximate it at, what did they say, at 2.8. So 2.8 minus 3 is negative 0.2. Negative 1/2 times negative 0.2. We'll have to add 1 to that to find the y value. So we get negative times negative cancels out. Half of 0.2 is 0.1 plus 1 ought to be 1.1. Any questions there on 31? Any other questions? That was the last one that was asked for.
I just have a real quick question about 36. Would we approach it to where we would do the integral first and then do the limit of whatever that ends up being, or would we do the limit part first, if that makes sense?
I did not hear which number you were talking about.
Oh, number 36.
Oh, 36. So should I do the integral or the limit first on 36. Let's see here. What is 36? Okay. No, you should do neither of those things. So the limit as h approaches 0 of 1 over h integral pi over 4 to pi over 4 plus h sine x over x dx. Oh, I'm gonna wait for the fraction to go by my house, and then I'll finish talking about this one.
Sorry, I didn't hear what you said.
I just said I was going to wait for the trash truck to go by my house.
Oh, okay.
All right, should be good now. All right, so what this is, first off, is this is the limit as h approaches 0 of the integral times 1 over the difference between these of some function. And so they've kind of got a lot combined going on here. But effectively what this is it's the limit as h approaches 0 of the integral of sine x over x. And so really what you want to do is recognize that this, if we took the integral of, if we pretended that we could and took the integral of sine x over x from pi over 4 to pi over 4 plus h, and then took the derivative of that, that would be the limit as h approaches 0 of that over this h value. So what it looks confusing, and probably what I'm saying is confusing, but maybe let me try it. Let me write it out this way. Let's let capital F of x. I'm sorry. Let's let capital F of x equal the integral from that's the best way to write this out. Let's write it this way. Let's do this. Let's let capital F prime of x. Let's say capital F prime of x is equal to sine of x over x. So we're going to call this function inside of here the derivative of some function capital F. And so then effectively what we'd have here is we'd have capital F prime of x inside of, I think it's going to hopefully this will make this easier to understand what I'm trying to say here. This one's a complicated one that I wouldn't necessarily expect to look quite like this on the AP test again. But the integral of f prime should just be capital F. So then effectively what we have is we have the limit as h approaches 0 of 1 over h times capital F of pi over 4 plus h minus capital F of pi over 4 all over pi over 4 minus pi over 4 plus h, sorry, pi over 4 plus h minus, yeah, sorry, just that, right? Yeah, that's good. I want this h to be inside of here, but I'll have it inside of there in a second. So right, this is just the integral of capital F prime is just capital F, evaluate the upper minus the lower. If I had this h inside of here, this is the limit as h approaches 0 of f of x plus h minus f of x all over h, right? So I'm gonna cancel this here, put it inside of here. And this is the limit definition of the derivative. Does that make sense? Right. The limit as h approaches 0 of a function at x plus h minus a function at x all over h. And from there, we can say this just means the derivative with respect to x of capital F of x evaluated at x equals pi over 4. And the derivative of capital F is f prime. So this ought to just be sine of pi over 4 over pi over 4. And the sine of pi over 4 is root 2 over 2 over pi over 4 should be 4 over pi. So you should end up with 2 root 2 over pi as your final answer. That's a messy one, using fundamental theorem of calculus and the limit definition of the derivative. I would be very surprised if you had to do something like that on the AP test. Does that make sense, though?
Yeah, thank you.
Yeah, sorry, as a kind of a convoluted answer there, but. Any other quick questions? Oh, we're over time, aren't we? Anybody have any quick questions? Are we all good?